So I recently stepped away from academic for the most part. And but during that period of my career, I was fortunate enough to have my intellectual life supported by a number of people. One of them is a co-author of this paper, Patrick, who was recently referred to by Alex Stringer as a savant. So, but I'm pretty much convinced that he is one of the top biostatisticians in Canada, those top 5. Another is John Brown himself, who has supported my intellectual life over the past decade. And both Patrick and I were blessed with 2 exceptional students that we'll be hearing from tomorrow. So Alex Stringer saying, I've never been able to pronounce it first. Right. Oh, wow. Okay, that's amazing. Okay, so I pretty much played a supporting role in this work. So I'm going to pass this over relatively quickly, Patrick. But I wanted to give you some kind of understanding of my involvement. Okay, so in 2017, I went over to my research office and I strolled by Patrick's office. And I found him seized with the following exercise, demonstrating that Gauss-Markov random fields can approximate Gaussian random. But he wanted to demonstrate this without using the stochastic partial differential equation approach, which was the route taken by Lindgren and others. And Patrick really viewed this paper as being a culmination of a long history in the statistical literature that's given there, and he'll take us through some of that history. And within it, what's interesting is that there are repeated analogies to time series. And so in the spirit of that history, Patrick wanted to demonstrate this result using by spectrum. So the strategy that he was developing was to demonstrate the result in dimension in time, and then try to figure out how to do the same calculation. And I really encouraged him to think about doing it in an arbitrary dimension. Because what I felt is that all of these calculations, as you might have already guessed, have a very common structure. And once you identify that common structure, then it's relatively easy to figure out how to do that. And that's what interested me about what he was trying to do. And also I'll talk about that. But the first question is, why would we do this? This is the known result. Why do we need to do this again? And but the problem, I don't know if it's a problem, but the fact is that statisticians usually don't have stochastic partial differential in their tools. But they often have spectral analysis plots. So by doing this, the result became accessible to, say, an ambitious undergraduate student. And the other reason we did it is that it was a really interesting way to weave this calculation into the statistical literature, which is, I think, what made this work open. So I just want to give you a flavor of the strategy that we used by just thinking about the simplest case. So in this case, we do the covariance matrix. Get the covariance matrix as a dense matrix. And we can also express through differencing operators the covariance matrix as a sparse precision. So the dense covariance matrix is an interesting theoretical result, but not useful for computations, but sparse precision matrix, which was the point. So so in our strategy, we want to think about how do we export calculations in one dimension, two dimensions. And so a useful technical thing to do was to express an autoregressive process, an AR1, as a conditional autoregressive. So this is a little bit weird because you're basically expressing an AR1 model or a realization in an AR1 model in both.
Sorry.
Yes.
You're speaking about.
Oh, well, I don't.
Because for us is not agree.
I'm sorry. I'm sorry.
For me.
Okay. Okay. Yeah. Not. So it. Yeah. So a lot of these questions will be answered when Patrick gives his portion of the talk. So we can delay satisfaction till then, or I can write something down on the blackboard. So it's so I'm going to write this right down. So it's this. So you have an observation in the present, and it depends on the most recent observation, but it doesn't depend on any. It doesn't depend upon any past observations. Okay. Okay. So I'm not going to remember. Pardon me. Auto regress. Yeah, auto regressive. And so the so this is the AR1 model, and the car model. The car model is a conditional autoregressive model, which we'll learn more about when Patrick gives his talk. But so in time series, it makes sense to talk about an observation depending on past observations. It doesn't make much sense to think about a present observation depending on both the past and the future. But in rewriting this AR1 model as a car model, it's exactly what we did. But it was it was for technical convenience. Okay. So, but what we found interesting, and Patrick put in that's okay, don't worry. But although it seems like a very odd thing to do, to run a time series in both the past and future, it actually does appear in the statistical literature in this paper, but in the there it appears. What he talks about a line transect. So you have space, and you know what people were trying to do at that time was to take the models that were well known for time series and try to figure out how to use them in space. So the line transect is basically this car1 model over a one-dimensional line in space. So that's something that it discusses. Okay, and I think I only have one more slide, and then I'm going to pass it. Oh no, I wanted to say one more. Sorry. So for the AR1, you have these two expressions for the covariance matrix, and they're both true. And so what we set about doing was showing that you could actually, through spectral analysis, demonstrate that the second expression is actually, even though we already know it's true. And the reason we did that is because we wanted to do the same thing in space, where you don't have a nice result. And delta is a differencing operator, and M is the Matern correlation. Okay. So yes. Yeah.
For special case.
Yes. Yes.
After it's space.
Well, it is. Yeah.
But it could conceptually take.
Yeah. So anyway, without going through all the calculations, though Patrick, I think, has some. Basically, the common structure of these calculations have distinct characteristics. And once you identify those, then the rest of the calculation just produces the potential. So much so that you might ask the question, why didn't we just use computer algebra for these calculations? And my experience with computer algebra is that it's very good if you have a complex calculation that has a structure that depends on only a few rules, and they get iterated. But this calculation was quite different because it depended on many rules. And they only get iterated. That's why. So I'm going to pass it over to Patrick for greater details. But before I do that, we did have a talk yesterday that had photographs of academics from recent. And what I want to say, so I thought this would be of interest to everybody. But what I want to say is that this gentleman is not a statistician and not a math, but he is the great-grandfather of, and he also is relevant to this university because in the 60s and 70s he was the chair of Arabic and Islamic studies at the university. And so he was famous for for his historical understanding of the 15th century. And if you were to come to Granada in the, say, 70s or 60s, 80s and 90s, there was a tourist guide that was based on historical accounts. Anyway, I mean, for me, it's kind of fun to be here, but given that, the great-grandfather of my children, a renowned professor. Okay, Patrick, over.
Put this thing on. Feel like a carnival marker. All right. Oh. Well then, I learned something new today. You can hear me? Thank you, Amy. And I think actually I'll start on this slide and go back to it. And ooh, I'm not switching. Okay. Oh, now I'm loud. All right. So yeah, I work with spatially things and not very much with splines, but luckily Jamie and I had a very clever student, Zhang, there, who does know splines and stochastic differential equations. So you can ask him any hard questions about anything you see here tomorrow. But, so I work on spatial problems, and I learned time series before spatial things. So that sort of affects how I look at this thing. And a simple introduction to spatial statistics is I have these things here that are random fields. So red is high values and blue is low values. And these things are, well, if you have a random field, they need to be correlated in a way. And the Gaussian distribution is really the only nice one that has nice correlation properties that work in a sensible way, or that's why we're dealing with Gaussian things. And Gaussian random fields can be characterized by a correlation function, which I have in the top. And the solid black correlation function is something that decays very quickly. And you get something that looks like this, that's pretty rough. And then the dotted line decays very slowly, and you get something like this, which is pretty smooth. And the typical statistical problem is you don't observe this whole field. And it was mining engineering where it started. You were looking for gold, and you dig a few core samples and measure gold at a few places, and you want to reconstruct the whole field. And coming back to another bit of too much on this slide to take it all in. So where we use these things is a model like this, where we have some data y that has some distribution pi, might be Gaussian or Poisson or a negative binomial. And the mean of that is lambda, and I might have a link function that could depend on some covariates, which is x of s, and then the u of s there is kind of stuff that's left over that our covariates don't account for. So it could be, if we're looking at number of cases of cancer, x would be covariates like smoking, and u is stuff that risk factors for cancer that we're trying to investigate, or u might be high in a place where there's a factory causing pollution, for instance. So we have these geostatistical models are one way of looking at spatial statistics, and this started sort of in the 1940s. And a parallel way of looking at spatial models are lattice processes, where we say, if I'm on a regular grid, the value in every grid cell depends on its neighbors. So instead of a correlation saying that cell and that cell are correlated depending on how far apart we are, we'd say the red cell depends on the blue cells that are next to it. and perhaps maybe the neighbors of the neighbors. So this would be a second order process. The red cell depends on the blue and the oranges. And here's a regular grid, or these were done more often with these irregular lattices. So these are census regions, and Toronto there, you might say, might depend on what its neighbors are, which are the blue ones and the neighbors of the neighbors. There's different ways of modeling spatial processes, and splines are another thing done from the beginning pretty much, thin plate splines, and they're all sort of related. So what's the difference between these two models? So we have a geostatistical model where we say we have a joint distribution that depends on, the covariance depends on distance, and as I get further apart, the covariance drops. Or I could say my point yi depends on all the other values, which are, so here I'm saying j not equal to I. So what's happening at cell I depends on all the other cells. And the Markov structure would say that actually I don't need to know all the other cells, I just need to know the neighbors, or the neighbors of the neighbors. And where we're going is there's an equivalence between the two of them, even in dimensions bigger than 2. And understanding the relationship is insightful, and the curse of dimensionality is one thing that came out of this. And there are some links to splines that I'll try to bring in as I can. Okay, so why would we want lattice processes? For me, it makes sense to look at covariances rather than lattice processes, especially because these grids, say, are artificial things, or I might have a 1 meter grid or a 1 foot grid if I'm working in America, or a 3 meter grid somewhere else. The grids are often pretty arbitrary, and I want a correlation that depends on kilometers or meters, that I can adjust them. Well, the lattice processes solve the curse of dimensionality. Is as you get more dimensions, from 1 dimension to 2 dimensions to 3 dimensions, you get a lot more data points, your covariance matrix gets a lot bigger, and these lattice processes, they're sparse, meaning every value only depends on its neighbors and not the whole area. So there are very efficient algorithms like Gibbs sampling that BIRS-IMAG showed in 1974 as a way you can simulate or do inference on these processes only looking at neighbors a bit at a time. Or you can calculate a likelihood function using the precision matrix, which is sparse, and more of that as we go along. So if I define a lattice process, something that depends on its neighbors, well, what is its covariance function? I mean, it's got to have one, or I hope it has one. So that's what we're looking at. And can we fit these computationally very nice sparse models to approximate these geostatistical models? And without using stochastic differential equations, there might be some mathematicians in this audience who are more comfortable with them than I am. And if you cast the thing as an SPDE, all the mathematics comes out in a nice way. For people like me, it's nice to try to do it without it. Okay. Yeah, okay, so a random thing in space. So by field, as opposed to a time series, would wobble up and down in time. And a random field is something that changes in 2 dimensions. So something like this. So every grid cell has a value. So a 2-dimensional process is what I mean by a random field. So these lattice processes are discrete. The geostatistical ones are continuous. I evaluated it at specific grid cells, but yeah, I can evaluate the correlation anywhere. I put them on a grid to make nice pictures. Yeah. So yeah, it's a continuously valued thing. But these lattice processes are sort of inherently discrete because everything depends on its neighbor, and I can't come in and stick a new cell over there or there. So they're unsatisfying in that way, but computationally, they're really, really nice. So can we get the best of both worlds? So here is, what's the simplest possible thing you could do to have a 2-dimensional process? So here's the autoregressive thing in time, is saying, to get from yesterday to today, I take yesterday's value, I multiply it by rho. So I'm scaling sort of, this is always less than 1. So I'm forgetting a little bit about what happened yesterday and adding some noise. It's the simplest thing you could do. What's the simplest thing you could do in space? Or you could set rho equal to 1 and you get a random walk. So in space, what's the simplest thing you can do? I could take a grid cell. What's its value there? I take the mean of its neighbors. I multiply that by theta, which is some scaling factor, so I forget a little bit of what my neighbors are doing, and then I add some noise on top of that. So it's really hard doing things in space, or especially in 1954 when computers weren't what they are now. So being able to do anything is an accomplishment, and even doing this is not simple unless you have modern computing. So you take the average neighbors, you shrink and you add noise, and this thing is, the top thing is a conditional distribution saying, if I know my neighbors, what am I doing? So the joint distribution here is if I say I take all these pixels, this is a 10 by 10 grid, so there's a vector of length 100. So this vector of length 100, what is that? It's normally distributed with mean 0, and P is the precision matrix. So the variance matrix is the inverse of P, and it has this nice structure here. But the next bunch of slides will go into more of this detail. But this is computationally very nice, because even if I'm on a 1,000 by 1,000 grid, so 1,000,000 entries in this variance matrix there, well, the inverse, most of it is 0, and I only get a few non-zeros. And so I can deal with very, very big matrices just because they're sparse. Yeah, so U is my random vector. So U1 is the value of in cell 1, U2 is the value in cell 2, U3 is the value in cell 3. Yeah, one long vector. Yeah, and I'm ordering them row-wise. You need to order them somehow. And so space doesn't behave as nicely as time for a lot of reasons. And one is it's not time, you can just write them in an order. There's no sort of natural ordering in space. So here's where we're going. And the history of cars, the first thing I found written on them was a paper by Paul Levy in 1948, where back in the 40s, the papers contained a lot of stuff. Yep. Sure.
You say mean because you take all UIs, right? But
yeah.
Those that's supposed to be farther to be affected less. In this you say mean of all of them, so those far away are affected the same way.
Okay, yeah, so I put something here. So this is the bit I glossed over. So this is twiddle. So GI and GJ. I is an observation. GI and GJ are the locations of the cells. And this is saying they're neighbors. So I'm interested in this. So I take all the cells that are neighbors. I take the mean of them.
Why do you need?
Well, you could do, and I was talking to someone who said, well, why don't I take the median or something else? If you take the mean, then the multivariate process has this nice distribution. Not everything you do gives you a multivariate distribution like that. And that's Julian BIRS-IMAG wrote about that, or that was his sort of contribution, saying sometimes you can do it. The Hammersley-Clifford theorem for the mathematicians is the thing that says what can and can't be used in a nice way. Because one model, the next most popular spatial model that's not Gaussian like this is the Ising model, where everything is a 0 or a 1. And any particular cell, you say, how many of my neighbors are 1? And each cell is Bernoulli distributed. And the more ones you have as neighbors, the more likely you are to get a 1. So that's another example. But there are surprisingly few of these things that are sort of actually used. And a lot. Got to satisfy Hammersley-Clifford theorem. That,
are the entries of P, right?
That's right, yeah. Oh, that's script and that's not, but yeah.
Yeah, so and this comes from the model description.
Yeah.
Inverse doesn't need to be sparse, but it doesn't. Right?
Yeah, so that we can do everything we need to with the inverse. Well, we need the determinant and everything. But yeah, so we will.
Talk about the neighbors.
Yeah. Wow, so to start with, this is just first nearest neighbors, but that's where we're going. We're going to expand the neighbors. Yeah, so we're getting there. So before I had a covariance function, and I said we can calculate the covariance matrix. Does it have a nice covariance function? I guess I skipped over the stationarity property. The covariance between 2 points depends only on their distance and not the rotation or the angle or anything else. There are models that do that, but start with stationary things. And Paul Levy said that any Markov process where everything just depends on its neighbors like that, the matrix, the first equation is what he has in his paper. This is my reordering of it. but the variance matrix must satisfy this property. So delta 1 is sort of the second differencing operator in the x direction, and delta 2 is the second differencing operator in the y direction, and your matrix sigma must satisfy that property. And then you reorder it and you get this thing here where p is the precision. So this was sort of known in 1948, and this paper by Whittle, 1954, is where the ideas were solidified a lot, and a lot of really interesting stuff in here. And it, well, as you'll see, didn't have much of an impact on the discipline until Lindgren and Rue and others in 2011. But this is also in Whittle's bit. He said, okay, this is delta S squared and delta Y squared. Eta is your process. And I say, for what's happening in this cell, I apply this thing, and then I have, this is like my autoregressive term, and then that, and these are independent. And so we had that written in there, and said, if you take it in continuous time, you get this SPDE, and ask Zhang if you want to know about that. But generally took it from here and went running. The first, so sigma is the variance matrix. Yeah. 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 A difference equation. I mean, so sigma is a big matrix. It's a variance matrix. Yeah.
Sigma is basically inverse of P also, right?
Yeah, that's right. So that.
The first equation is inverse of P.
Yeah, I mean, yeah. So P there is really sigma inverse. Yeah. So, okay, so Levy had this, and Whittle formalized it a bit, saying it's actually obeying this thing, and then you write it that way. And we will spend more time on this. But then he said, actually, if you look at the variance, he said, you use this funny identity in here from Titchmarsh, where you have this weird integral, and then there's a Bessel function and whatever. And we deduced from the scheme. You couldn't get away with this these days. There's a lot of stuff that goes from A to B to C. Rho is the covariance function. And the covariance function R is distance. So the covariance between two grid cells depends on their distance, and it's this R K1 of R. So this is a Bessel function, and this is actually the M function here, the Matern function, except no one called it that at the time. But the result is a CAR1. So the simplest thing you can do is a Gaussian Markov random field, and it has covariance, this thing. So we know the covariance function. So if you want to fit something with this covariance function because you don't believe the grid accurately represents what you're actually measuring, you can use the grid anyways and think of it as a computational trick. So is it useful? And BIRS-IMAG 74 paper said you can do, actually, you don't need the whole sigma matrix. You can do all your calculations separately, kind of one cell at a time, looking only at the neighbors of those cells. And you do that repeatedly and cycle and cycle and cycle, and you get the sort of samples and inference of the full process. And Moran in 83 and BIRS-IMAG 1981 said, yes, the CAR1 is, they put the CAR1 explicitly in their model. If your eyes are good, you'll say, hey, but he has a K1 here, and this is a K0. And that's because actually Finn Lindgren explained this to me. So thanks, Finn, that what Whittle was looking at was actually a SAR1 and not a CAR1. He wasn't conditioning on everything else. But after we go through a few things, it'll become a bit more different. But actually the CAR1 is this K0, which has an infinite spike, which is maybe what you're getting about earlier. That doesn't make a lot of sense. But the BIRS-IMAG and Mondel said this is actually a De Vries process, who looked at mining things in South Africa in 1951. So people knew about this, and it wasn't really used at all. And why is that? Well, it is too rough. It's not very useful. And Matern in 1960 said, this is a really good correlation function, which has the Bessel function in it. And it has really nice mathematical properties because this new parameter here controls the differentiability. So in K sub 1 is differentiable once, a Matern with nu is equal to 2 is differentiable twice. As you go to infinity, you get a Gaussian, infinitely differentiable. And then if nu is a half, you get an exponential. So in Whittle's 64 paper, then he elaborated on this a bit and said, actually, we can have, this is pretty much what he had before in the earlier paper, but he's powering up this difference operator by a power p. And he says, if you do that, you get this covariance function, which is that one there. So we can, if you think the K0 or the CAR1 is too rough, we can make it smoother doing this.
So so we were starting with discrete model on one side, and
Yeah.
continuous on the other side, but through differential equation, you get continuous on both sides.
Yeah, so I guess, yeah, as you make these grid cells smaller and smaller and smaller, then the difference operator becomes continuous. And yeah. Yeah, and yes, and is that, and n is the dimensionality. Yeah. For a given p, yes. So that's the second last slide. Yeah. Yeah, so smoothness can mean alpha also affects smoothness. And if alpha is sort of the autoregressive bit. So if rho is close to 1, you don't forget very much and you get things smooth. And you can think of it as a scale parameter. You need to have something like an alpha to say, if you change your coordinates from miles to kilometers, you don't want to change the properties of everything in your process. So if S is in miles and I change it to kilometers, I multiply alpha by 1.4 and everything's the same, nothing changes. So that's where the alpha comes in here. In a way, it scales the distance. So that controls the correlation, and the P controls the differentiability. So they're both roughness in a way. You can have something smooth because it's strongly correlated, or also smooth because it's differentiable. Phi. This thing here, I think it's 1 over alpha, or is it actually alpha? So phi is like a scale. So the term depends on 2 parameters, phi and nu, and phi is a scaling parameter. Again, if I change r from kilometers to miles, then I make phi bigger. If phi is very big, it means the correlation falls very slowly. If phi is 1,000, it means r can get really big and I'm still correlated. Whereas if this is really small, my correlation drops quickly. So m it's actually square root of 2 times nu. And it's a deterministic scaling function that we use to put everything on the same scale. And that's a bit of a FUD tip. Originally, m is equal to 1, but then that means things change when you change nu. It wasn't very nice. And, but that, again, we'll work on that as we go along. So when did this actually become useful and people actually use it? Julian BIRS-IMAG, the late and very interesting Julian BIRS-IMAG, did all kinds of stuff with these Markov random fields on grids and wrote all about the equivalence, and no one paid any attention really until this paper, Lindgren et al. 2011. Then this changed the world pretty quickly in terms of doing spatial statistics. We used to be inverting variance matrices, and it really limited the size of the problem we could have. A 1,000 by 1,000 grid would be a 1 million by 1 million variance matrix, absolutely intractable. Then when this stuff came along, wow, we can actually work on 1,000 by 1,000 grids. And again, this is starting to be related to thin plate splines. And this is a graph you often see in their paper where in here, they took that stuff from Whittle, but put it in an SPDE and worked out things through formulas that I don't use in the next slides. And this is one of the slides saying I'm looking at all these points in Germany and I've measured something there and I want to do inference on this process. And I take a bunch of basis functions that are tent functions here. And so each vertex here, you'll look at these different tent functions and you model the coefficients on the tent functions to make a long story short. And then you can do that using all these equations to approximate something like this. Isn't this great? So then it really took off. So summary of part 1, We can use GMRFs to fit geostatistical models. And if you're comfortable with SPDEs, you are probably quite happy with the derivation in Lindgren's paper. It wasn't useful until it was generalized, until you went up to higher orders. And then, yes, you can start making smooths. All right, so we're going to go from dimension 1 to 2 to n. And here is your first order autoregressive thing over there. If I write this in matrix form, so U is my random time series from 1 to n, it satisfies this equation here. So at any point, I take U1 plus minus rho times U at time -1, and that is Z. I'm just taking that thing and writing it in this form here. And this is the first order autoregressive model. The first thing you learn in a time series course as an undergrad is if you look at several steps ahead, you get rho to the power of h, and the covariance function is a kind of an exponential function. So we can do that the easy way, or we can do it the hard way. And we're going to do it the hard way because we want to do this in space as well. And Whittle here talked about the line transect, and he said, in time, you can say every observation depends only on the past. That makes sense in time, that you don't depend on what's happening tomorrow because it hasn't happened yet. You can't do that in space. In time, you can say there's only one direction backwards. In space, you can't do it that way. There's no way of ordering things in a satisfactory way. So he says, well, suppose we have a spatial process, but we're traveling along a line. How does that behave? I shouldn't really just look at, if I'm going up here, this side of the line, I should look at the other side of the line as well. And then I can generalize that in space. So here's your autoregressive, and then here, so this is the car, the conditional autoregressive, and you're looking at the future as well as the past. Right, so we're going to rewrite our AR model as a car model, saying, if I'm interested in what's happening at a specific time point, conditional on everything else, it's actually all I really need to know is what happened tomorrow and what happened yesterday. I don't need to know anything else if I'm in a first order process. And you can rewrite the car model up above. I take the mean of my two neighbors, multiply it by phi is really an AR model. If that's rho in the AR, this is what you have in a car. The same process. And the precision matrix has this form here, because we're glossing over this. It's a graphical model, and there's theory of graphical models, what the precision matrix should be, and it's 0 if you're not neighbors, and it takes these entries here, which is actually the second difference operator. So the precision matrix has this formula. And so how do we get from this precision matrix here to working out the variance matrix? Hey, where are we? Well, let's look at things by looking at the Fourier basis function. So I create some matrix B of Fourier coefficients, and the talks yesterday and today have got me thinking a lot about orthogonal basis functions, and I haven't worried about orthogonal splines before, but there's a lot of advantages to orthogonality, and well, this is one of them here. And this matrix B has the property that yes, it's orthogonal, orthonormal even, but also if I apply this, delta could be either the second difference operator, or if you're happy with continuous time, it could be the continuous difference operator, or this 1 minus 2, 1. If I take this operator and apply it to the matrix B, I get this thing here. I can move B to the other side in a way. The derivative of a sine is a cosine, and the derivative of a cosine is a sine. So if I take the second derivative, I'm going to get my original thing back. But then the F here, this is a diagonal matrix of frequencies. And this delta here is the size of your grid. But anyways, it's a nice, B has this property that it's orthonormal. And also if I apply delta to it, I can move B to the other side, which is good. So if I do that, and a bunch of math, but I said sigma is P inverse, and I'm going to put a BB transpose in here because it's the identity, and then I can move this B to the other side, and I get an F squared there. And the F is a diagonal matrix with frequencies, and if I change this matrix thing into a sum, a specific entry of that matrix has this form, so I'm summing over all the rows and columns of B. So two tricks we do. First is we have sines and cosines. We'll use an identity to turn those just into a cosine. Some things pop out. And then the second thing, we convert this sum to an integral, which means you get a Jacobian. And then the second thing you do is you look up in Gretchen and Rizhik or Abramowitz and Stegen or whatever your favorite such thing is. What is this ruddy thing? Well, it's that. So we proved that an autoregressive has an exponential covariance function, doing it the hard way. So, but we want to make this thing smoother. The first order car is too rough to be practical. It's not differentiable at all. So I'm going to power up this precision matrix. So here's my precision matrix, and I'm going to take it to the power of P, which is like Whittle powering up the difference operator. And so if that's my precision matrix, then U is actually a car process. And in time here, it has this form here. So I'm still in one dimension, but if I'm powering things up to the power of P, then what's happening depends on P values in the past, not just 1, but 3 if P is 3, and it's an autoregression of order P with these coefficients here. So it does depend on the past, but we're saying there's really only one parameter that matters, or there's only one parameter that determines the coefficients. If P is 3, I get 3 coefficients, but they're all some deterministic function of rho, and we can do all the same stuff we did earlier. So we put that B matrix in the middle here, convert the sines and cosines to cosine only with an identity, and then we look up this funny thing in some tables of identity, and we get this equation here, where that thing is a P minus a half down there. That is here. Yeah. Yeah, so we're in one dimension. So it's this thing. So Matern P minus a half. So I can, if I make P bigger, if I make P 3, this is going to be differentiable twice. But I'm subtracting a half there. But I think this is a natural 3-parameter time series. I have one parameter, which is the variance, how big it gets from 0. The second one is this phi parameter here, which I'm dividing this by phi. So if I change from seconds to minutes or whatever, I can control this correlation. And the third parameter is the differentiability. So that's a way of, I mean, an AR, I could do a completely general AR with any coefficients, but this is a way of saying I only have 3 parameters. One controls differentiability, the other correlation, and the third the variance. And why does this matter? Well, the trick is we can do this same trick in space, moving to the car. So yeah, the trick is the car is really you're taking an average of neighbors, and an average of neighbors is actually a second difference operator, and we can diagonalize things with spectral analysis and do all this in space. So here's a spatial car. In space, the value of UI at a particular grid cell depends on the mean of your neighbors. So I'm the first order process here, and then you scale it down towards 0, and I get this precision matrix P with these entries in it. And that means P is, I can write it this way, this thing, or I can write this way. I get this thing on the diagonal and this thing, delta 1 and delta 2 differencing in x and y directions. So here's a spatial car with P is 2. I mean, I chose a fairly coarse grid here just so you could see the cells, but I could do this at 1,000 by 1,000. But here we're starting to get things with P is equal to 3. This sort of looks smoothish. This thing here kind of could be anything. It doesn't look very correlated. But now you make P bigger, you start getting things like smooth and so on. And I can make really nice pictures, you know, with these ones. So this is the precision matrix of a spatial car of order P, where everything depends on your neighbors, and then the neighbors of the neighbors, and the neighbors of the neighbors of the neighbors, if it's P is equal to 3. So we'll do spectral analysis in space, where we have basis functions, sines and cosines in the x and y direction, and I have a cosine going down like that, and a cosine going up like this, and in various different ways, and some at different frequencies. And this difference operator stuff, again, Still matters if I take delta times B, it's actually B times F with this thing on there. Where F is a diagonal matrix. And well, that's the covariance function. Well, the same trick as before. If I wrote out the matrix multiplication, I'd have sines and cosines. You apply this identity to get cosines only. Now there's a new trick in here. You change the integral to polar coordinates. And the polar coordinates, d alpha and r, and that thing kind of reduces. If you do it in 2 steps, there's a Bessel J function, but it still comes down to the matern here. So we're in business. We can do spatial cars and we can make them smooth. And if you want a matern correlation function, you can have one. I'm going to fit a car because sparse precision matrices, I like those, but I'm getting the matern as my answer. Okay. So here's a graph of the black is the matern correlation as calculated from the actual formula. And these dots are, I create a precision matrix on a grid and I invert it and look at the correlation. So there is a sizable discrepancy here where P is equal to 2 right at the origin as P. It looks not so bad here. The approximation isn't terribly good at the at lag 0, but it gets much better as you move away from it. Okay, what next? I know I should be looking at the clock. More spatial dimensions and 3-dimensional things, or in computer experiments and other things, they might have 30 dimensions and they do use materns. Could they be doing this? I can still say my UI depends on take all the neighbors of grid cell I and all these 30 dimensions and add some noise onto it. And your P matrix would look like this, where D is the number of dimensions. I can create sines and cosine basis functions, run through all the same thing, and I get this crazy big integral. And I have to integrate over all 30 dimensions. And here's, in our paper, we say you convert that into hyperspherical coordinates, where you have all these different angles, and you transform them this way and you get a Jacobian, and when you go through at the end of it you get a matern correlation function in multiple dimensions. And this is, as you were asking earlier, you had this P and D over 2 and whatever. So this is sort of the insight that came out of this is, yeah.
So like I can see how we get P minus 1 and 2 variables. It's not good if we have P minus 1 now.
Yeah.
Do it twice.
Hmm. Yeah, yeah, okay, yeah, so that's, but also, so this needs to be positive, and that's what I was hoping you weren't going to spill the beans about the first time around. P needs to be bigger than D over 2 to do something sensible. So if I'm in 30 dimensions, I need to look at least 15 neighbors. So that is showing this is actually not as useful in higher dimensions. You need to look, as the dimensionality gets bigger, you need to look at more and more and more neighbors. So I think that's what I have in here. So what does it mean? So here's our matern correlation function with this thing here. So the cursive dimensionality was, Bellman, I think, was the first one to use it. And he said, what it means is if you have as D gets bigger and you're in more dimensions, if you want to capture, say, 10% of your observations, the proportion of a box that contains that 10% gets bigger and bigger as P gets bigger. You need to add a lot more stuff. Hasty and Tibshirani took that, that was Hasty and Tibshirani in 1996. That's the cursive dimensionality. If I take a cube-shaped region and I want 10% of the box, that cube-shaped region is going to get really, really big really quickly in higher dimensions. Whereas Bellman said the cursive dimensionality is just, as you go in more dimensions, then the size of this gets bigger. If I'm on a 10 by 10 grid, in 1 dimension, 10 time points, a 10 by 10 matrix. In space, that's 100 by 100. In 3 dimensions, 1,000 by 1,000. That's 10 by 10 has no resolution, and that's blowing up quickly. But Hasty and Tibshirani are saying it's not so much about the number of observations and the size of the matrix. It's you need size of the length 1 over C to the power of D, and they're talking about the sparsity of the precision matrix. So as you go above 2, the precision matrix gets less and less sparse. In 30 dimensions, you need at least 15 neighbors, and those are 15 neighbors in 30 dimensions. So there's kind of a lot of them.
There are also more neighbors,
Yeah.
more points.
Yeah, that's right. There's a lot more points, and a lot of them are neighbors. So that, so yeah. Okay. Well, I think this is my either second last slide or last slide. So what are some limitations? Irregularly spaced data. Everything's irregularly spaced, but you can say, well, there's just missing values. That's fine. I'm on a grid, but I'm missing a few things. But then is it better to use basis functions? And currently the thing that's done by, well, everyone except me, because I use the Markov random fields, uses these tent basis functions, because that's within the INLA software, and that's what can be done easily. And the spatiotemporal, another thing is, in space, we have 2 dimensions, and it makes sense to think of them as just 2 things. Time and space are sort of different, or to say, my distance between here and that point tomorrow, I shouldn't just take some Euclidean thing, even if I rescale stuff. So in space and time, it's not really just 3 spatial dimensions. So separable models and an autoregressive in time, and we do that. So in conclusion, I think, so thanks everyone for the comments, because I thought I'd be done early. So I'm glad we had these going on. I think we've made a non-technical understanding about these processes. At least I can understand the relationship between Markov random fields. The average of neighbors is actually a second difference thing, and that's a geostatistical model as we make the cells smaller. And the GMRF, it delays the cursive dimensionality. It kind of gets rid of Bellman's problem of saying sigma gets big because it's sparse. But eventually, Hastie and Tibshirani's cursive dimensionality is going to hit you if your dimensions go big. Okay, so thanks, and we got some papers. And have we got questions? Well,
let's reverse our thinking. So we have bathroom covariance, process with matrix covariance.
Yeah.
We have, so this process, if you specify points, which we have certain covariance, which is expressed by general covariance function, which can take any point. And we're looking at the inverse of this matrix.
Yeah.
Because this is discretized now already, inverse. So so we look, but for the bathroom covariances, you have very explicit and nice and Fourier transform.
Yeah.
So you have Fourier transform, which is much better than the matter covariance because it is at least explicit function. Here we have those more complicated Bessel functions.
Yeah.
So can one use this simple Fourier transform to answer what is the inverse of the covariance matrix?
Well, so we could go the other way. So in a way, we said you have a Markov random field and we derive the matern.
So the matter, we have Fourier transform on matter, but from that, can I use Fourier somehow to get the inverse of the covariance matrix as specified point?
Yeah, so if I know the Fourier transform is something, can I create the precision matrix in a nice way?
I don't know.
Yeah, I mean, the key thing about the precision is it's really sparse, and what really matters are where the zeros are. So I think there isn't an intuition in there that says the frequencies at certain things cancel in a lot of cases, and you get zeros a lot of the time, I guess is what would be the interesting thing. But yeah. No, but
because the simplicity of this Fourier transform is kind of
yeah, I think that the real mathematical thing would be if I have matern, which SPDE gives you the matern as a solution? What's his second difference operator? And then based on the SPDE, I can get the precision, or I can get Fourier or basis function coefficients. It's the way it's done, rather than. Oh, I guess, can you get from the Fourier transform to the SPDE in some nice way? I think that's probably it. Maybe Zhang will correct me, but I think actually, if you have, it's not too hard to relate a Fourier transform to an SPDE, I think. Okay. Okay, I'm glad I'm right about that one. Okay.
So I don't know if it's related, but does the word cellular
I read about them a bit many years ago. It was kind of the thing people were saying, and agent-based models for infectious diseases is what that's related to. Yeah, like many statisticians, I had to learn about infectious disease epidemiology pretty quickly about 5 years ago. Yeah.
but they don't use average.
Yeah, we have a conditional independence, or what makes infectious disease models kind of not suitable. These models are good for chronic diseases. We could say me and my neighbor might have similar risk because we're exposed to different stuff. For infectious diseases, if my neighbor is sick, then they will give it to me. And my neighbor might have high risk, but they didn't get sick, in which case I don't care. Or that's that. There's a conditional independence that we use these things for that are good for chronic diseases. But when you have direct dependence because somebody's transmitting it, it sort of doesn't work this way. And then it depends on how many things are. This Markov structure doesn't work as nicely. But these infectious disease models do. They put all these differential equations down and so on. But yeah, there's a conditional independence here that makes everything nice. Okay.